Look up at the night sky. What do you see? Countless stars, each a sun, some with planets orbiting them. Our galaxy, the Milky Way, is home to billions of stars, and the universe contains billions of galaxies. The sheer scale of the universe is difficult to grasp. It stretches out in every direction, farther than we can see. In this vast expanse, is it possible that our planet is the only one with life? Are we truly alone in this cosmic ocean? For millennia, we saw the stars as fixed points of light, weaving them into our myths and legends. But with the invention of the telescope, our understanding began to change. We could see more stars, fainter stars, farther away than ever before. As our technology advanced, so too did our understanding of the cosmos. We discovered new planets, moons, and galaxies. And yet, the question still lingers. Are we alone? The more we learn about the universe, the more profound that question becomes. In 1950, physicist Enrico Fermi posed a simple yet profound question. Where is everybody? This question, known as the Fermi Paradox, highlights the discrepancy between the high probability of extraterrestrial life existing and the lack of any contact or evidence for such life. The universe is about 13.8 billion years old, plenty of time for intelligent civilizations to have arisen and potentially traveled across the galaxy. Yet we found no definitive signs of their existence. No radio signals, no alien artifacts, no spaceships on our doorstep. There are many possible solutions to the Fermi Paradox. Perhaps intelligent civilizations are rare, and we are among the first to emerge in the Milky Way. Maybe interstellar travel is simply too difficult or impractical, even for advanced civilizations. Or perhaps intelligent life has a tendency to destroy itself before it can reach out to the stars. The Fermi Paradox forces us to confront our assumptions about the nature of intelligence, technology, and our place in the cosmos. In 1961, astronomer Frank Drake devised an equation to estimate the number of detectable civilizations in our galaxy. The Drake equation is a series of factors that, when multiplied together, give a rough estimate of the number of civilizations capable of communicating with us. It considers factors like the rate of star formation, the fraction of stars with planets, and the likelihood of life evolving into intelligent beings. While the Drake equation doesn't provide a definitive answer, it serves as a valuable tool for guiding our search. It highlights the key areas where we need more information and encourages us to think critically about the factors that might influence the development of life beyond Earth. The search for extraterrestrial life is ultimately a quest to understand our place in the cosmos. It's a journey driven by curiosity, fueled by imagination, and shaped by the fundamental human desire to explore the unknown. The Fermi Paradox, at its heart, is about the silence. Given the universe's age and size, Fermi argued, there should be signs of intelligent life everywhere. Yet we haven't found a single concrete piece of evidence. No alien messages, no spaceships on the horizon, no giant structures orbiting distant stars. This silence is what makes the Fermi Paradox so perplexing. Some argue that the silence is to be expected. Space is vast, distances are immense, and the chances of two civilizations being technologically advanced at the same time are astronomically slim. But even taking those factors into account, the silence remains a puzzle. There's a sense that given enough time, some signal, some sign of extraterrestrial activity should have reached us by now. And yet, the universe, for all its splendor and vastness, remains stubbornly silent. One of the most significant hurdles in understanding the Fermi Paradox is the immense scale of both time and distance in the universe. The universe is 13.8 billion years old. If compressed into a single year, all of human history would be confined to the last few seconds of the last minute on New Year's Eve. The closest star to our Sun, Proxima Centauri, is over 4 light-years away. Even traveling at the speed of light, it would take more than 4 years to reach it. Other star systems are hundreds, thousands, or even millions of light-years away. This combination of vast distances and the finite speed of light means that communication between even relatively close civilizations would be incredibly challenging. Imagine sending a message to a civilization 1,000 light-years away. It would take 1,000 years for your message to reach them, and another 1,000 years for their reply to return. The scale of time and distance in the universe presents a significant barrier to contact. The universe may be teeming with life, but the vastness of space and time could be acting as an effective cosmic insulator, keeping us in the dark for now. Another possible explanation for the Fermi Paradox lies in the concept of great filters. This idea suggests that there are certain critical thresholds that life must cross to evolve into a technologically advanced civilization. These filters could take many forms. One possibility is that the emergence of life itself is incredibly rare. Another filter could be the development of complex life. While single-celled organisms may be relatively common, the leap to multicellular life could be a hurdle that few life forms ever clear. Even more daunting is the possibility of filters that lie ahead of us. Perhaps there's a natural limit to how long technological civilizations can survive before succumbing to self-destruction. If so, it's possible that other civilizations have arisen in the past, only to wipe themselves out before they could reach out to the stars. The concept of great filters forces us to consider the fragility of life and the challenges that lie ahead. The Fermi Paradox is not a paradox in the strictest sense. It's more of a puzzle, highlighting the vastness of what we don't know about the universe. While the lack of detectable signals from extraterrestrial civilizations is intriguing, it doesn't necessarily mean that we are alone. Our search for extraterrestrial intelligence is still in its infancy. We've only been actively listening for radio signals for a few decades. Our technology for detecting other potential signs of life is constantly improving. It's possible that we simply haven't been looking in the right places or with the right tools for long enough. Our understanding of life itself is constantly evolving. Life can exist in incredibly extreme environments on Earth, suggesting that life elsewhere could be far more diverse and adaptable. The Fermi Paradox serves as a reminder of the incredible scale and mystery of the universe. It challenges us to confront our assumptions about the nature of life, intelligence, and our place in the cosmos. The universe is vast, filled with billions of stars. Finding another civilization among all those stars is akin to finding a single grain of sand on a beach. This is where the Drake equation comes in. Developed by astronomer Frank Drake in 1961, it's a framework for thinking about the possibility of intelligent life elsewhere in the universe. The Drake equation considers factors like the rate of star formation, the fraction of stars with planets, and the likelihood of life evolving into intelligent beings. The first step is to consider how many stars are being formed each year in our galaxy. The more stars that form, the more chances there are for planetary systems to arise, and within those systems, the potential for life. The Drake equation also factors in the percentage of those stars that are similar to our Sun, stars that are stable and long-lived enough to potentially support life on orbiting planets. Thanks to advancements in astronomy, particularly the Kepler Space Telescope, we now know that planets are incredibly common in the universe, with many stars hosting multiple planets. Our Sun is a complex furnace where lighter elements are fused together to create heavier elements like carbon, oxygen, and nitrogen, the building blocks of life. The Drake equation considers the percentage of stars that have enough of these heavy elements to potentially give rise to life-bearing planets. These heavy elements are scattered throughout the cosmos when stars explode as supernovae, seeding the universe with the ingredients necessary for life. The Drake equation then narrows down the search further by considering the fraction of those stars with heavy elements that actually have planets orbiting them. Not all stars are fortunate enough to have planets swirling around them. Thanks to advancements in astronomy, we now know that planets are incredibly common in the universe, with many stars hosting multiple planets. Having a planet is one thing, but having a planet that can support life is quite another. This is where the concept of the habitable zone comes in. This is the region around a star where the temperature is just right for liquid water to exist on the surface of a planet. The Drake equation factors in the number of planets that might exist within the habitable zone of their star. But even within the habitable zone, the emergence of life is not guaranteed. The Drake equation acknowledges this by considering the fraction of those habitable planets where life actually arises. This is perhaps the most uncertain factor in the equation, as we only have one example of life arising on a planet, our own. We don't yet know if life is a cosmic fluke or a natural consequence of the laws of physics and chemistry. The search for life beyond Earth continues, driven by our curiosity and desire to understand our place in the universe. Section 4. Intelligence, a cosmic imperative. The Drake equation doesn't stop at just the emergence of life. It goes a step further and considers the fraction of life-bearing planets where that life evolves into intelligent life. This is a significant leap, as intelligence, at least as we define it, is not a given outcome of evolution. Think of all the diverse species that have existed on Earth. While many are remarkably adapted to their environments, only one has developed the kind of intelligence that has allowed it to build tools, develop language, and contemplate its own existence. The Drake equation acknowledges that intelligence might be a rare occurrence, even on planets teeming with life. It's possible that intelligence, at least the kind that leads to technological civilizations, is not an inevitable outcome of evolution, but rather a fortunate accident, a product of specific environmental and evolutionary pressures. This part of the equation is like checking which of our specked marbles have developed a unique pattern or color, signifying the emergence of intelligence. It forces us to ask whether intelligence is a universal constant, a natural stage in the evolution of life, or a cosmic outlier, a rare and precious phenomenon. Section 1. Listening for whispers. For centuries, humanity could only dream of finding life beyond Earth. We gazed at the stars, wondering if other beings looked back at us. With radio astronomy, we could listen for whispers from distant worlds. Projects like SETI scan the skies for signals from intelligent civilizations. Imagine a vast, silent ocean. Radio astronomy is our lighthouse, piercing the cosmic darkness. It's like tuning a radio dial, searching for a clear station. Each frequency band is a potential channel of communication. The challenge is sifting through the vast electromagnetic spectrum. Section 2. Seeking new worlds. Finding life beyond Earth means finding the planets where that life might exist. The search for exoplanets has revolutionized our understanding of the universe. We've discovered thousands of planets, each adding to the tapestry of possibilities. Imagine exploring a vast forest, searching for a specific flower. You could wander aimlessly or use a map highlighting likely areas. That's what the search for exoplanets is like. Telescopes like Kepler and TESS find planets by looking for tiny dips in a star's brightness. These dips indicate a planet passing in front of the star. Analyzing these dips helps estimate a planet's size, orbit, and atmosphere. This data helps identify potentially habitable worlds. Finding a potentially habitable planet is just the first step. The next challenge is to determine if it actually harbors life. This is where the search for biosignatures comes in. Biosignatures are substances or phenomena that provide evidence of life. They are signs that life has left its mark on a planet. Imagine footprints in the sand. You know someone was there. Biosignatures are like those footprints, evidence of life. While biosignatures offer clues about the presence of life in general, technosignatures are specifically focused on detecting signs of advanced technology. These are the signals that would indicate not just life, but intelligent life capable of harnessing technology in ways that could be detectable across interstellar distances. Imagine you're walking through a forest and you stumble upon a perfectly straight line of trees. While it's possible that this could occur naturally, it's far more likely that it's the result of human intervention, a sign that someone intentionally planted those trees in that pattern. Technosignatures are like that line of trees, suggesting a deliberate, intelligent hand at work. Technosignatures could take many forms, from radio signals like those sought by SETI, to large-scale engineering projects such as Dyson spheres, hypothetical structures built around stars to capture their energy. Other potential technosignatures include laser emissions, industrial pollutants in a planet's atmosphere, or even the heat signatures of massive, energy-intensive civilizations. The search for technosignatures is still in its early stages, and it's limited by our current technology and understanding of what forms advanced alien technology might take. However, it's a field of growing interest, driven by the possibility that the most compelling evidence of extraterrestrial intelligence might not be biological but rather technological in nature. The search for life beyond Earth, whether through listening for signals, searching for habitable planets, or seeking biosignatures or technosignatures, faces one fundamental challenge: the vastness of space and time. The universe is incredibly old and incredibly large, and the distances between stars are so immense that they are difficult to comprehend. Imagine you're trying to have a conversation with someone standing on the opposite side of a vast canyon. Your voices are too faint to carry across the distance, and even if you shout at the top of your lungs, it will take a long time for your words to reach the other side. That's the challenge we face when searching for signs of life in the cosmos. Even if we detect a promising signal or find a planet teeming with life, the chances of interacting with that life in real time are slim. The time it takes for signals to travel through space means that any communication would likely be delayed by years, centuries, or even millennia. This challenge of distance and time is not insurmountable, but it requires patience, perseverance, and a willingness to think on cosmic timescales. The search for life beyond Earth is a marathon, not a sprint, and it requires a long-term perspective that spans generations. Imagine the headlines: "Scientists confirm extraterrestrial life." The discovery would be revolutionary, shaking the foundations of our understanding of the universe and our place within it. For scientists, it would be a dream come true, the culmination of centuries of speculation and decades of dedicated research. But it would also be just the beginning. The first order of business would be to learn everything we could about this newfound life. The discovery of extraterrestrial life would revolutionize science and have profound implications. It would shatter our anthropocentric view, forcing us to confront our place in the universe. Dialogue between science and religion would take on new urgency. Ultimately, it would be a humbling experience, reminding us of our place in a vast, interconnected universe. Section 3: Societal Upheaval and New Philosophies. The news of alien life would explode into the public consciousness, becoming the biggest news story in human history. Governments and organizations would scramble to understand the implications and formulate a response. Existing societal structures might be challenged, leading to new philosophies and ideologies. The arts and popular culture would be equally transformed. Section 4. The unification of humanity. The discovery of extraterrestrial life could unify humanity. Our differences might seem less significant. We share a planet in a vast universe. Imagine a world where international conflicts are set aside. Collaboration would become essential. We would pool our knowledge and resources. The discovery could spark a renewed focus on science. Young people might flock to STEM fields. It would be a defining moment in human history, a challenge, an opportunity, and a source of endless wonder. Section 1. A universe of wonder. The universe is a place of astonishing scale and beauty. From the birth of stars to the dance of galaxies, the cosmos unfolds with grandeur. Are we alone? This question drives our curiosity. The search for life reflects our desire to explore and understand our place in the universe. Section 2. Our place in the cosmos. The search for life beyond Earth has profoundly impacted our understanding of ourselves. It forces us to confront our place in the cosmic order and consider the possibility of a universe teeming with diversity. This realization is humbling and exhilarating. It reminds us we are part of something much larger. The search for extraterrestrial life is ultimately a search for ourselves. It's a quest to understand our place in the cosmos. So as you gaze up at the night sky, remember the universe is filled with wonder and mystery. The search continues, and the answers will be awe-inspiring.